The Unexplored Deep, a journey to the last frontier on Earth. Close your eyes for a moment and imagine standing at the edge of the world, not on some distant mountain peak or windswept cliff, but here, right here, on any shoreline you've ever known. Feel the sand between your toes, still warm from the day's sun. Listen to the gentle whisper of waves as they kiss the shore, each one carrying secrets from places no human eye has ever seen. Now, let that gentle tide pull your imagination outward, past the breakers, past the familiar blue that stretches to the horizon. Beneath those rolling waves lies the greatest mystery our planet still holds, a world so vast, so unexplored, that we know more about the surface of Mars than we do about the depths of our own oceans. Tonight, we are going to journey together into the story of why the deep sea remains our planet's final frontier. We'll walk alongside the dreamers and inventors who dared to imagine diving deeper than any human had gone before. We'll feel the crushing weight of water that has kept us from our own blue planet's secrets. And we'll discover why even now, in an age of satellites and smartphones, 95% of our oceans remain as mysterious as they were to the very first humans who gazed upon the sea. The ancient gaze. Picture, if you will, a young girl standing on the shores of the Mediterranean some 4,000 years ago. Her name has been lost to time, but her wonder lives on in every human heart that has ever stared into deep water. The bronze tools of her civilization gleam in the morning light, and behind her, the great ziggurats of her people rise toward the heavens. Yet before her stretches something far more mysterious than any earthly monument. She watches the fishermen push their reed boats into the shallows, their nets heavy with the day's catch. But she sees something they've forgotten to notice, how the clear blue water grows darker and darker until it becomes a blue so deep it's almost black, a blue that seems to swallow light itself. "What lives down there, grandfather?" she asks the old man mending nets beside her. He pauses in his work, his weathered hands still for a moment. "Child," he says, his voice carrying the weight of all human wondering, "down there live the dreams of the sea gods. Down there, the water becomes so heavy it could crush the strongest cedar boat. Down there—" He trails off, looking out at that impossible blue. "Down there might live everything we've ever imagined, and more that we never could." This moment, this exact moment of wonder mixed with impossibility, has repeated itself in every civilization that ever touched the sea. The ancient Greeks believed the ocean floor was the realm of Poseidon himself, too sacred and terrible for mortals. Homer, in his great epics, spoke of the wine-dark sea as a realm where gods and monsters dwelt in equal measure, where the very water could transform men into legend or destroy them entirely. The Phoenicians, those brave sailors who dared to venture beyond the Mediterranean, still spoke of the deep sea in whispers, as if the very water might hear them and take offense. They mapped coastlines and established trade routes that spanned thousands of miles, yet they never lost their reverence for the deep waters that lay beyond their keels. Their ships carried offerings to Yam, the god of the sea, and their sailors bore tattoos that were believed to protect them from the monsters that dwelt in the deepest places. In ancient Egypt, priests of Sobek performed rituals at the edge of the great river, casting precious objects into the deepest pools as offerings to the crocodile god who ruled the underwater realm. They believed that the Nile's depths connected to a vast underground ocean that stretched beneath all the land, a mirror image of the sky above, but populated by beings of immense power and alien intelligence. The Chinese spoke of dragon kings who lived in crystal palaces beneath the waves, controlling the weather and the tides from their coral throne rooms. The Japanese fishermen left offerings at seaside shrines, praying for protection from the kami of the deep, Spirits so powerful that merely thinking about them incorrectly could bring typhoons or sea monsters to destroy entire villages. But it wasn't just fear that kept humans from the depths. It was physics itself, cold, inexorable, and absolute. Ancient philosophers, observing how objects became harder to retrieve as they sank deeper into pools and wells, began to understand that water itself became an enemy at depth. They noticed how even strong swimmers would struggle at depths of just a few body lengths, how the pressure would build in their ears and lungs until they were forced to return to the surface. Aristotle, in his systematic way, attempted to catalog what was known about the deep sea. He wrote of creatures that lived in the middle depths, fish with strange eyes and peculiar behaviors that differed from those caught near shore. He theorized that the deepest parts of the ocean must be inhabited by forms of life so alien that they would be unrecognizable to surface dwellers. He wrote, "The sea is like the night sky, vast, dark, and filled with wonders that dance just beyond the reach of human understanding. But unlike the stars, which we can at least observe from afar, the sea's depths remain hidden beneath layers of water that grow heavier with every cubit of depth, until they become impenetrable as stone." This understanding, that water itself became the guardian of the deep sea's secrets, would define human interaction with the ocean depths for millennia to come. Every civilization that touched the sea developed its own explanation for why the deep waters remained unexplored, but all shared the fundamental recognition that the sea's depths represented a realm governed by different laws than the familiar world of air and sunlight. The weight of water. Let me tell you something that will change how you see every glass of water, every raindrop, every ocean wave. Water, that gentle substance that cradles life, becomes something altogether different when it gathers in the deep places of the earth. Imagine you're holding a single drop of morning dew. It weighs almost nothing, sits perfectly round and crystal clear on a blade of grass. Now imagine another drop joining it, and another, and millions more. At first, they simply pool together, harmless as a puddle after rain. But as more water gathers, something remarkable begins to happen. Each drop above presses down on the drops below. Gently at first, you could swim through 10 feet of water, 20 feet, even 50 feet, with nothing more than the breath in your lungs and the strength of your limbs. But the sea doesn't stop at 50 feet. It doesn't stop at 100, or 1,000, or even 10,000. In some places, the ocean floor lies more than 6 miles below the surface. 6 miles of water, each drop pressing down on those below with inexorable patience. To truly understand this crushing weight, imagine standing beneath a column of water reaching from the sea floor to the surface. At just 33 feet below the surface, the pressure of all that water above doubles the pressure your body feels. At 66 feet, it triples. By the time you've descended just 300 feet, the height of a modest skyscraper, the pressure would crush your lungs like empty paper bags. Consider what this means in concrete terms. At sea level, the atmosphere exerts a pressure of about 14.7 pounds per square inch on every surface. Your body doesn't notice this because you're adapted to it. Your internal pressure balances the external pressure perfectly. But in water, this delicate balance becomes impossible to maintain. For every 33 feet you descend, the pressure increases by another 14.7 pounds per square inch. At 330 feet, the depth that some recreational divers reach with specialized equipment, the pressure is about 10 times greater than at the surface. At 3,300 feet, it's 100 times greater. And at the deepest point in the ocean, nearly 36,000 feet down in the Mariana Trench, the pressure exceeds 15,000 pounds per square inch, more than 1,000 times the pressure at sea level. To put this in perspective, Imagine placing a car on top of every square inch of your body. That's approximately the pressure experienced at the bottom of the deepest ocean trenches. It's a force so immense that it would instantly compress any air-filled space to almost nothing, would crush any ordinary material like tissue paper, and would squeeze the water out of any living tissue not specifically adapted to withstand it.
This crushing pressure is why air-breathing animals cannot simply hold their breath and swim to great depths. The air in their lungs would compress until their chest cavities collapsed. The air spaces in their ears and sinuses would implode. The gases dissolved in their blood would behave in strange and dangerous ways, potentially forming bubbles that could kill them if they returned to the surface too quickly. Even more remarkably, this pressure affects not just living things, but the water itself. Deep ocean water is actually denser than surface water, compressed by the immense weight above it. A cup of water from the deepest ocean trenches, if somehow brought to the surface while maintaining its compressed state, would be noticeably heavier than a cup of surface water. The pressure also affects temperature in counterintuitive ways. While we might expect deep ocean water to freeze under such pressure, the opposite is true. The pressure actually lowers the freezing point of water, allowing it to remain liquid at temperatures that would form ice at the surface. At the deepest parts of the ocean, water can remain liquid at temperatures below 32 degrees Fahrenheit. This is why the deep sea remained unexplored for so long, not because humans lacked courage or curiosity, but because water itself became our gentle jailer, growing heavier and heavier with each foot of depth until it could squeeze the life from any unprotected human body. The ocean's depths were protected not by monsters or gods, but by the simple, inexorable physics of water under pressure. Ancient divers, working without any breathing apparatus, learned these lessons through painful experience. Pearl divers in the Persian Gulf, ama divers in Japan, and sponge divers in the Mediterranean all developed techniques for descending to depths of 100 feet or more, but they could stay down for only minutes at a time, and they paid a terrible price in injury and death. The legendary ama divers of Japan, mostly women who dove for abalone and pearls, developed extraordinary lung capacity and techniques for conserving oxygen underwater. They could descend to depths of 80 or 100 feet and remain submerged for more than 2 minutes. But even these remarkable athletes could not venture much deeper without risking their lives to the crushing pressure of the depths. Greek sponge divers, working in the Aegean Sea, developed a technique called the stone, using heavy stones to help them descend quickly to the sea floor, then dropping the stone and swimming rapidly back to the surface. This allowed them to reach depths of 150 feet or more, but the pressure at these depths often caused permanent injury. Many sponge divers suffered from the bends, decompression sickness, caused by nitrogen bubbles forming in their blood as they rose too quickly from depth. These early divers were humanity's first explorers of the deep sea, but they were also living proof of their dangers. Their techniques allowed them to glimpse the mysteries that lay beneath the waves, but the crushing pressure of the depths ensured that these glimpses were brief and costly. First dreamers. But humans, wonderful humans, have never been content with impossibility. If we couldn't go down to the sea, then by all the gods of invention, we would find a way to bring a piece of our world down with us. It was the year 1691, and in a small workshop in London, a man named Edmund Halley, yes, the same Halley whose comet graces our skies, was bent over a peculiar contraption. Picture him there, in the flickering candlelight, his hands stained with tar and brass polish, his mind racing with possibilities that would have seemed like magic to anyone else. What he was building looked, to the untrained eye, like a wooden barrel, but this barrel was lined with lead and fitted with windows of thick glass. It was, he believed, a way to trap air underwater, to create a pocket of the surface world that could travel into the depths. Halley's diving bell, as he called it, worked on a principle so simple it was elegant. Air, being lighter than water, would remain trapped in the upturned vessel even when submerged. A person could crawl inside this wooden womb and descend beneath the waves while still breathing the air of the world above. But Halley's innovation went beyond the basic diving bell design that had been attempted by others. He understood that the air inside would gradually become foul as the occupant breathed it, converting oxygen to carbon dioxide. His solution was ingenious. He connected the main bell to smaller barrels of fresh air, which could be released into the bell as needed. This early life support system allowed for much longer underwater stays than had ever been possible before. The first test must have been terrifying. Imagine Halley himself climbing into that barrel, feeling it lift from the dock by crane and rope, then watching through the thick glass windows as the familiar world of sunlight and seabirds faded away. The water grows darker, colder. The pressure begins to press against the wooden walls with a force that makes them creak and groan like living things. At 10 feet below the surface, the pressure would have been noticeable, a tightness in the ears, a sense of the air inside becoming denser. At 20 feet, the wooden staves would begin to compress slightly, and the glass windows would bear an increasingly heavy load of water pressure. At 40 feet, every joint and seam in the barrel would be under tremendous stress. But it worked. For a few precious minutes, Halley had done what no human had ever done before. He had visited the underwater world and returned to tell about it. He descended 60 feet below the surface, far enough to see fish swimming in perpetual twilight, far enough to witness the way sunlight fractures and dances in the deep water like fragments of broken gold. In his careful notes, Halley described the experience. The light above grew dim and green, as if seen through colored glass. Fish of strange appearance swam past the windows, some curious enough to approach this wooden intruder in their realm. The silence was profound, broken only by the creaking of the barrel and the sound of my own breathing, which seemed unnaturally loud in the confined space. Yet even in his triumph, Halley understood the limitation of his achievement. 60 feet was remarkable, yes, but the deep ocean descended for miles beyond that. His diving bell was like a candle held up to illuminate the night sky. Brave and beautiful, but hardly enough to explore the vast darkness beyond. More importantly, Halley had proved that the fundamental challenge of deep-sea exploration could be overcome through engineering. Word of Halley's success spread quickly through the scientific communities of Europe. Other inventors began experimenting with their own innovations of diving bells, each trying to improve on the basic design. Some added better air supply systems. Others experimented with different materials and shapes. A few attempted to add mechanical arms that would allow the occupant to manipulate objects on the seafloor. The diving bell represented more than just a technological achievement. It was a philosophical breakthrough. For the first time in human history, the ocean depths were no longer completely inaccessible. The realm of Poseidon and the Dragon Kings had been invaded by human ingenuity. The deep sea was no longer purely mythological. It was becoming a place that could be visited, observed, and eventually understood. But these early diving bells also revealed just how alien the underwater world truly was. Every dive brought back reports of strange sights, forests of seaweed swaying in underwater currents, fish with behaviors unlike anything observed near the surface, and most mysteriously of all, hints of much deeper mysteries lying beyond the reach of the diving bells. Divers reported seeing the seafloor drop away into darkness so complete that their lights could not penetrate it. They described currents and temperature changes that suggested vast systems of water movement in the depths. Most intriguingly, they brought back samples of water, sediment, and sea life that hinted at complex ecosystems existing far below the limits of diving bell exploration. The philosophers of pressure. As the centuries turned, other dreamers took up the challenge. Each generation built upon the wisdom and failures of those who came before, like a great conversation carried on across time itself. In 1776, the same year that American colonists declared their independence from Britain, a clockmaker named John Smeaton was declaring his own independence from the limitations of diving bells.
In his workshop, surrounded by the precise gears and springs of his trade, Smeaton was applying the same methodical thinking that went into his timepieces to the problem of underwater exploration. He understood what Halley had discovered, that air could be trapped underwater, but only temporarily. The air in a diving bell would gradually become stale and unbreathable as the person inside consumed its oxygen and exhaled carbon dioxide. Smeaton's innovation was beautifully simple. He would pump fresh air down from the surface. Picture the scene: a diving bell suspended from a ship above, connected to the surface world by a leather tube through which fresh air was constantly pumped by hand. A team of men on deck worked in shifts, operating bellows that forced surface air down through the tube to the diver below. For the first time, a person could remain underwater not just for minutes, but for hours. Smeaton himself descended to depths of 20 fathoms, 120 feet, and worked there in the green twilight, building the foundations for lighthouses and harbor walls. But more than just extending the duration of underwater work, Smeaton's system revealed new aspects of the underwater world that had never been observed before. With hours instead of minutes to spend underwater, divers could observe the behavior of sea life in much greater detail. They watched schools of fish moving through the water in complex patterns, following currents and food sources invisible from the surface. They observed how marine plants and animals changed their behavior throughout the day, even in the perpetual twilight of the depths. Most significantly, Smeaton's divers began to understand that the underwater world was not static but dynamic. Currents flowed at depth, sometimes in directions opposite to surface currents. Temperatures changed with depth in predictable patterns. The seafloor itself showed signs of constant change: sediment moving, organisms growing and dying, the landscape slowly transforming over time. But even Smeaton's improved diving bell could only take humans so far into the deep. The wooden vessels, no matter how cleverly constructed, could only withstand so much pressure before the crushing weight of water would force its way through every seam and joint. At depths beyond 200 feet, the pressure would compress the wood so severely that the diving bell would begin to leak, then flood catastrophically.
It was around this time that natural philosophers, as scientists were then called, began to truly understand what they were fighting against. They calculated the pressure at various depths, measured how materials behaved under crushing force, and gradually came to a sobering realization: the deep sea wasn't just unexplored because of lack of trying. It was unexplored because the very physics of water made it one of the most hostile environments imaginable. Robert Boyle, the famous physicist and chemist, conducted a series of experiments that demonstrated how gases behaved under pressure. His law, that the pressure and volume of a gas are inversely related, explained why diving bells could only descend so far before the air inside would be compressed beyond the point where humans could breathe it effectively. At the deepest parts of the ocean, they calculated, the pressure would be over 1,000 times greater than at the surface. It would be like having the weight of 50 jumbo jets pressing down on every square foot of surface. No material they knew of could withstand such crushing force, while still allowing a human to survive inside. These calculations led to a period of deep pessimism about the possibility of deep-sea exploration. Some scientists concluded that the deepest parts of the ocean would forever remain beyond human reach. Others suggested that only the most robust mechanical devices might someday be sent into the depths, but that humans would never be able to accompany them. The French mathematician and physicist Pierre-Simon Laplace wrote extensively about the mathematical impossibility of human survival at great depths. The ocean's depths, he concluded, are as inaccessible to man as the interior of distant stars. The physical laws that govern pressure and the compression of matter ensure that there will always be a limit to human exploration of the underwater realm. Yet even as scientists calculated the seemingly insurmountable barriers to deep-sea exploration, inventors continued to dream of solutions. They experimented with stronger materials, better air supply systems, and more robust designs for diving vessels.
They began to understand that overcoming the pressure of the deep sea would require not just incremental improvements to existing designs, but entirely new approaches to the problem of keeping humans alive underwater. Some proposed using metal instead of wood for diving bells, reasoning that steel or iron might withstand pressures that would crush wooden vessels. Others suggested that the solution might lie not in making diving bells stronger, but in making them smaller and more specialized, with just enough room for a single person and the most essential equipment. A few visionaries even suggested that the ultimate solution might require abandoning the diving bell concept entirely. Instead of taking a room full of air underwater, why not find a way to extract air from the water itself, like fish do? This line of thinking would eventually lead to some of the most important innovations in underwater breathing apparatus. But all of these innovations still lay in the future. For the moment, natural philosophers and inventors were left with the sobering realization that the deep sea represented one of the most challenging frontiers that humanity had ever attempted to explore.
The Age of Iron and Dreams. The 19th century brought with it the romance of iron and steam, of great ships that could cross oceans, and railways that could span continents. It was an age when humans began to believe that no frontier was truly insurmountable, that every mystery could be solved with enough engineering and determination. In 1837, a German inventor named Augustus Sieb was working in his London workshop on a problem that had plagued diving bell operators for decades. The bells could descend, yes, but they were clumsy and limiting. A person was trapped inside a wooden box, able to look but barely to move, like a bird in a cage. Sieb's solution was revolutionary in its simplicity. Instead of taking a room underwater, why not take just the essential part, the air that surrounds a person's head? His invention, the diving helmet connected to an air pump on the surface, freed divers to walk along the sea floor while still breathing surface air. The standard diving dress, as it came to be known, consisted of a waterproof canvas suit with weighted boots and a bronze helmet that completely enclosed the diver's head. Air was pumped down through a hose from the surface, and exhaled air escaped through valves in the helmet. The diver could move freely on the sea floor, limited only by the length of the air hose and the strength of the surface crew operating the air pump. Picture those first helmet divers, looking like visitors from another world with their great bronze heads and weighted boots. They could descend to depths of 200 feet, 300 feet, even 400 feet in some cases. They walked through underwater forests of kelp that swayed in the current like trees in an eternal wind. They saw fish that lived in perpetual twilight, creatures adapted to a world where the sun was nothing more than a dim green glow far above. For the first time, humans were not just visiting the underwater world, but exploring it, working in it, beginning to understand its alien beauty and strange laws. Helmet divers built pier foundations in harbors around the world, salvaged cargo from sunken ships, and constructed underwater installations that would have been impossible to build from the surface. The advent of helmet diving also led to the first systematic exploration of underwater ecosystems. Divers could spend hours on the seafloor, carefully observing and documenting the behavior of marine life. They brought back detailed descriptions of underwater landscapes, biological specimens that had never been seen by surface dwellers, and increasingly sophisticated understanding of how the underwater world functioned. But even these brave divers in their bronze helmets could only scratch the surface of the deep ocean's mysteries. At depths beyond 500 feet, the pressure became too great for their equipment. The air hoses would collapse under the water pressure, the helmets would be compressed until they no longer fit properly, and the canvas suits would be crushed against the diver's body with potentially fatal force. More troubling still were the physiological effects of breathing compressed air at depth. Divers began to report strange symptoms during deep dives: confusion, euphoria, and impaired judgment that could lead to fatal mistakes underwater. This condition, later known as nitrogen narcosis, was caused by the effects of breathing nitrogen under high pressure. Even more dangerous was decompression sickness, or the bends,
which occurred when divers ascended too quickly from deep dives. The high-pressure air they had been breathing dissolved large quantities of nitrogen in their blood and tissues. If they rose too quickly, this dissolved nitrogen would form bubbles in their circulatory system, causing excruciating pain, paralysis, and sometimes death. The physiology of diving became an area of intense study as doctors and diving specialists tried to understand why some divers could work safely at depth, while others suffered terrible injuries. They learned that the human body could adapt to increased pressure, but only within certain limits, and only if given time to adjust gradually. These discoveries led to the development of decompression tables, mathematical formulas that calculated how long a diver could remain at various depths and how slowly they must ascend to avoid decompression sickness. These tables represented some of the first systematic understanding of how the human body reacted to the extreme conditions of the underwater environment. Meanwhile, in the laboratories and studies of the world's great universities, marine biologists were beginning to ask questions that would drive the next century of ocean exploration. When they pulled up nets from deep water, they found creatures unlike anything that lived near the surface. Fish with huge eyes adapted to eternal darkness, creatures that glowed with their own cold light, organisms that seemed to belong to a different planet entirely. Where did these creatures come from? What did the deep ocean look like? What other life forms might exist in the deepest places of the sea? Places where the pressure was so great that it would crush any land creature instantly. Charles Darwin, in his revolutionary work on evolution, was fascinated by these deep-sea specimens. He recognized that the creatures living at great depths had evolved in isolation from surface life, developing unique adaptations to survive in conditions of perpetual darkness, crushing pressure, and near-freezing temperatures. The deep sea, Darwin wrote, represents a world as separate from our own as if it existed on another planet. The creatures that dwell there have followed evolutionary pathways that diverged from surface life millions of years ago. Studying these organisms may teach us as much about the possibilities of life as any discovery we might make among the stars. These questions burned in the minds of scientists, like a gentle fever, driving them to attempt what many considered impossible: to find a way to carry human observers safely into the deepest parts of the ocean. The age of iron and steam had given them new materials and new power sources. Now they needed to apply these tools to the ancient problem of exploring the sea's depths.
The sphere that defied the depths. The year was 1930, and off the coast of Bermuda, something unprecedented was about to happen. A steel sphere, barely large enough to hold 2 people, was being lowered into water so deep that sunlight had never touched its bottom. Inside that sphere sat 2 men whose names would become legend among ocean explorers. William Beebe, a naturalist whose writings had already inspired a generation to wonder about the natural world, and Otis Barton, an engineer whose quiet genius had made this moment possible. The sphere they called the bathysphere was Barton's answer to the crushing pressure of the deep sea. Instead of fighting the water's weight with air-filled chambers that could be crushed, he had created a solid steel ball with walls 3 inches thick. The sphere had no air pumps, no connection to the surface except for a telephone line and a steel cable. It carried only the air that was sealed inside it when the hatch closed, and 2 men brave enough to trust their lives to calculations and craftsmanship. The design of the bathysphere was deceptively simple, but every detail had been calculated with mathematical precision. The spherical shape distributed the water pressure equally across the entire surface, preventing the concentration of stress that had destroyed earlier diving vessels. The steel walls were thick enough to resist compression even at depths of half a mile or more. The single entrance hatch was held shut by the water pressure itself. The deeper they went, the more tightly the hatch would seal. But simple as the concept was, the execution required extraordinary precision. The steel had to be perfectly uniform in thickness and strength. The slightest flaw or weak spot would become a point of catastrophic failure under the immense pressure of the deep sea. The spherical shape had to be mathematically perfect. Even small deviations from a true sphere could create stress concentrations that would crack the steel like an eggshell. Barton, working with the best metallurgists and engineers of his day, spent months perfecting every aspect of the design. The viewing windows were made of fused quartz, the only transparent material known that could withstand the pressure they expected to encounter. The electrical connections for the telephone and lights had to be sealed with unprecedented precision to prevent water from entering the sphere. As the bathysphere descended past 200 feet, then 500 feet, then 1,000 feet, Beebe's voice crackled over the telephone line to the surface, describing wonders that no human had ever seen before. The blue-green twilight gave way to a darkness so complete that it seemed solid. But it was not empty darkness. In the beam of their searchlight, strange creatures drifted past like living stars. Jellyfish that pulsed with cold light, fish with teeth like needles and eyes like glowing coals. At 500 feet, they encountered the first creatures that Beebe had never seen before. Transparent fish that seemed to be made of living glass, their organs visible through their crystalline bodies. At 800 feet, they saw squid with bioluminescent displays so complex that Beebe compared them to underwater fireworks shows. At 1,000 feet, they entered what Beebe called the realm of eternal night. Here, the only light came from the creatures themselves. Fish swam past their windows, carrying patterns of lights like constellation maps. Jellyfish pulsed with rhythmic displays that might have been forms of communication. At 1,426 feet, deeper than anyone had ever gone before, Beebe's voice came up from the depths with an observation that would capture the imagination of the world. The only other place comparable to these marvelous nether regions must surely be naked space itself, out far beyond atmosphere, between the stars. The comparison was more apt than Beebe realized. Like space, the deep sea was a realm where humans could survive only inside sealed vessels, completely dependent on artificial life support systems. Like space, it was populated by forms of life so alien that they challenged basic assumptions about biology and survival. And like space, it was so vast that even the most ambitious exploration efforts could only scratch the surface of its mysteries. During their record-breaking dive, Beebe and Barton observed and documented dozens of species that had never been seen alive by human eyes. They watched the behavior of deep-sea creatures in their natural environment, free from the trauma of being hauled to the surface in nets. They saw bioluminescent displays of such complexity that they realized the deep sea had its own forms of communication and interaction that surface science had never suspected. But the bathysphere also revealed just how little humans knew about the deep ocean. Every dive showed them creatures they had never imagined, living in conditions that seemed impossible for life to endure. And yet, life was there, abundant and strange and beautiful. The deep sea was not the barren desert that many scientists had expected, but a thriving ecosystem with its own energy sources, its own food webs, and its own evolutionary pathways. The success of the bathysphere proved that humans could indeed travel to the deep ocean and return safely. But it had also revealed just how vast and alien that world truly was. Each dive showed them creatures they had never imagined, living in conditions that seemed impossible for life to endure. And yet, life was there, abundant and strange and beautiful.
But the bathysphere, revolutionary as it was, could only descend to about half a mile deep. The deep ocean, they were learning, extended much farther than that. In some places, the seafloor lay more than 6 miles below the surface, depths that would crush even Barton's steel sphere like an empty can. The bathysphere represented both the greatest triumph and the greatest limitation of 1930s technology. It had opened the door to deep-sea exploration, but it had also revealed just how much deeper that door led. The deepest ocean trenches lay miles below the bathysphere's maximum depth, and the creatures living there remained as mysterious as ever.
At such pressures, even tiny flaws in the vessel's construction could prove catastrophic. The crewsphere had to be inspected with unprecedented care, every weld x-rayed, every component tested beyond its theoretical limits. The life support systems had to be designed to function flawlessly for the many hours the dive would require. The ballast and buoyancy systems had to work perfectly in conditions no engineer had ever tested before. The dive was planned with military precision. Every aspect of the descent and ascent was calculated and rehearsed. Emergency procedures were developed for dozens of potential failures. Weather conditions were monitored constantly since the dive could only be attempted in perfectly calm seas. On January 23, 1960, Jacques Piccard and U.S. Navy Lieutenant Don Walsh climbed into Trieste's steel sphere and began their descent into Challenger Deep. The dive would take them through every layer of the ocean, from the sun-drenched surface waters to the eternal darkness of the deepest trench. As they dropped through the water column, they passed through layers of the ocean that told the story of our planet's depth and complexity. First came the sunlight zone, where photosynthesis was still possible and familiar sea life thrived. Schools of fish moved through the blue water like living clouds. Sea turtles and dolphins occasionally swam past their porthole, curious about this strange metal intruder in their realm. Then came the twilight zone, where the last traces of sunlight faded into perpetual darkness. Here, the first bioluminescent creatures began to appear: jellyfish that pulsed with cold light, fish with glowing lures, squid that communicated through complex patterns of bioluminescence. The water itself seemed to come alive with points of light that flickered and danced in the eternal twilight. Deeper still, they entered the midnight zone, where the only light came from the creatures themselves. This was a realm unlike anything on Earth's surface, a world where evolution had taken radically different paths, where creatures had developed senses and abilities that seemed almost supernatural. Fish with eyes like telescopes, designed to gather every photon of available light. Predators with jaws that could unhinge to swallow prey larger than themselves. Creatures so transparent they were virtually invisible except for their glowing organs. At 20,000 feet, they were deeper than most commercial aircraft fly. The pressure outside their steel sphere was more than 600 times greater than at the surface. Any unprotected human body would be crushed instantly to a fraction of its normal size. Yet Trieste continued its steady descent, its ballast systems working perfectly, its crewsphere maintaining the comfortable pressure and temperature of a surface laboratory. At 30,000 feet, they had descended farther below sea level than most mountains rise above it. They were now in the deepest layer of the ocean, the Hadal pelagic zone, named after Hades, the ancient Greek realm of the dead. Here, the pressure was so great that even the water itself behaved differently than at the surface, compressed into a form denser than normal seawater. And still, they continued down into pressures that no life on the surface could possibly survive. The walls of the trench rose around them like the sides of an enormous canyon, their surfaces marked by the slow accumulation of sediment that had drifted down from the surface over millions of years. Finally, after nearly 5 hours of descent, Trieste touched the bottom of Challenger Deep at a depth of 35,813 feet, almost 7 miles below the surface. The pressure outside their steel sphere was over 1,000 times greater than at sea level, sufficient to crush any unprotected object instantly. The bottom of Challenger Deep was a landscape unlike anything on Earth's surface. Fine sediment accumulated over millions of years formed a soft bottom that showed the imprints of strange currents and the tracks of unknown creatures. The water was crystal clear, filtered by its passage through miles of ocean above. And yet, even at this ultimate depth, life persisted.
Through their small porthole, Picard and Walsh observed flatfish and other creatures moving along the seafloor, proof that life had found a way to adapt even to the most extreme conditions on Earth. These creatures had evolved under pressures that would instantly kill any surface dweller, in perpetual darkness, in near-freezing temperatures, feeding on the organic matter that drifted down from the world above. The discovery of life at the bottom of Challenger Deep was perhaps as significant as the achievement of reaching it. It demonstrated that Earth's biosphere extended to literally the deepest accessible places on the planet. No environment, no matter how extreme, was completely beyond the reach of life's incredible adaptability. Their stay at the bottom lasted only 20 minutes, long enough to take photographs, make observations, and collect a small sample of sediment. Then they began the long ascent back to the surface, a journey that would take nearly 3 hours. As they rose through the layers of the ocean, they passed again through the various zones of marine life, each adapted to its particular depth and pressure range.
The problem, they later discovered, was with the ballast release system. The steel shot that was supposed to drop cleanly from the vessel had clumped together due to corrosion from seawater, making it difficult to release in a controlled manner. The crew managed to reach the surface safely, but the experience taught them that every system on a deep-diving vessel had to be designed to work flawlessly under conditions unlike anything found on the surface. Auguste Piccard used the lessons learned from FNRS-2 to design an improved bath escape called FNRS-3, which was later sold to the French Navy and renamed Trieste. This vessel incorporated dozens of improvements based on the experience with the first bath escape. The ballast system was redesigned to prevent clumping. The gasoline tank was modified to handle pressure changes more efficiently. The crew sphere was enlarged and equipped with better life support systems. But Piccard's greatest contribution to deep-sea exploration wasn't just the bath escape itself, it was the philosophy behind it. For the first time, humans had a vessel that could explore the ocean depths with complete independence from surface support. The bath escape could dive to any depth, remain there for hours, and return safely without requiring cables, air hoses, or constant communication with the surface. This independence opened up possibilities for ocean exploration that had never existed before. Instead of being limited to areas directly below a surface ship, bath escape crews could explore underwater mountain ranges, follow deep-sea currents, and investigate geological features that were miles away from any surface reference point. The bath escape also represented a new approach to the fundamental challenge of deep-sea exploration. Instead of trying to build vessels strong enough to resist the crushing pressure of the depths, Piccard had created a vessel that used the principles of buoyancy and ballast control to move through the water column like a fish. The pressure was still there, but the vessel worked with it rather than against it. The deepest place on Earth. By the 1950s, oceanographers had mapped the general contours of the sea floor using sonar and other remote sensing techniques. What they discovered was a landscape as varied and dramatic as any mountain range on land. Underwater canyons deeper than the Grand Canyon, mountain ranges that dwarfed the Alps, and in the Western Pacific, a series of trenches that descended to depths that seemed almost impossible. The deepest of these trenches, located near the island of Guam, was named Challenger Deep, after the British research vessel HMS Challenger that first measured its approximate depth during the famous Challenger expedition of 1872-1876. Early estimates suggested it was more than 6 miles deep, deeper than Mount Everest was tall. It was, quite literally, the deepest accessible place on Earth. The Challenger expedition itself deserves recognition as one of the most important scientific voyages in history. This British naval research vessel spent nearly 4 years circumnavigating the globe, conducting the first systematic survey of ocean depths, temperatures, currents, and marine life.
The expedition's findings filled 50 volumes of scientific reports and laid the foundation for the modern science of oceanography. Using hemp rope weighted with cannonballs, the Challenger's crew took depth soundings at 362 stations around the world. It was painstaking work, lowering miles of rope into the depths, waiting for it to hit bottom, then hauling it back up by hand. At one station in the Western Pacific, near what is now known as the Mariana Trench, they measured a depth of over 26,000 feet. It was the deepest sounding ever recorded at that time. But the Challenger's crew also made another discovery that would prove equally important. At every depth they tested, even in the deepest trenches, they found evidence of life. Their dredges brought up creatures from depths where scientists had believed nothing could survive. The discovery that life existed even in the deepest parts of the ocean would drive deep-sea exploration efforts for the next century. For Jacques Piccard, Auguste's son who had inherited both his father's engineering genius and his passion for exploration, Challenger Deep represented the ultimate test of the bathyscaphe principle. If a human-piloted vessel could reach the bottom of the deepest ocean trench and return safely, then truly no part of Earth's oceans would remain beyond human reach. Working with the U.S. Navy, which had acquired the bathyscaphe Trieste from Auguste Piccard, Jacques began preparations for what would be the deepest dive in human history. The challenges were immense. Challenger Deep was not just deep, it was more than 35,000 feet below the surface, a depth where the water pressure exceeded 15,000 pounds per square inch.
The Swiss Dreamer and the Floating Balloon. Sometimes the most revolutionary ideas come from the most unexpected places. In the mountains of Switzerland, far from any ocean, a professor named Auguste Piccard was thinking about the deep sea while floating high above the Alps in a balloon. Piccard was a balloonist and inventor who had already set records for high-altitude flight, ascending into the stratosphere to study cosmic rays and the thin upper reaches of Earth's atmosphere. But his mind was always working on new problems, new frontiers to explore. One day in the early 1930s, as he floated in his pressurized gondola high above the mountains, Piccard had a revelation that would change ocean exploration forever. He was looking down at the Earth from the edge of space, protected from the deadly environment outside by nothing more than a sealed metal chamber. The parallels struck him immediately. The challenges of exploring the deep ocean were remarkably similar to those of exploring the upper atmosphere. In both environments, humans faced crushing or explosive pressure differentials. In both, they needed to carry their life support systems with them. In both, they were surrounded by a medium that could kill them instantly if their protective chamber failed. The main difference was the direction of the pressure differential. In the stratosphere, the pressure inside the gondola was greater than outside. In the deep ocean, the pressure outside would be greater than inside. But there was one crucial difference that Piccard's balloonist mind immediately grasped. In the atmosphere, he used ballast to control his ascent and descent. To go up, he dropped weight. To go down, he released gas. What if the same principle could be applied underwater? This insight led to Piccard's most revolutionary invention, the bathyscaphe. Unlike the bathysphere, which hung from a cable like a bucket in a well, the bathyscaphe would be a free-diving vessel that could control its own descent and ascent. It would use gasoline, which is lighter than water and doesn't compress under pressure, as ballast, and steel shot that could be released to control buoyancy. The concept was elegant in its simplicity. A large tank filled with gasoline would provide buoyancy, just like the gas bag of a balloon. Suspended beneath this tank would be a pressure-resistant sphere to hold the human crew. To descend, the vessel would take on water ballast or release gasoline. To ascend, It would drop steel shot or release more gasoline. The entire system would be self-contained, requiring no connection to the surface. But turning this concept into reality required solving dozens of technical challenges. The gasoline tank had to be designed to allow water to enter as the gasoline was compressed by pressure, but without allowing the two fluids to mix. The ballast system had to be reliable, even under crushing pressure and in complete darkness. The crew sphere had to be even stronger than the bathysphere, since it would be expected to reach much greater depths. Working with his son Jacques, who had inherited both his engineering talents and his passion for exploration, Auguste Piccard spent years perfecting the bathyscaphe design. The first prototype, completed in 1948 and named FNRS-2 after the Belgian research fund that sponsored it, looked like nothing anyone had ever seen before. The vessel resembled an underwater dirigible, a massive float tank nearly 50 feet long filled with 28,000 gallons of gasoline, with a small steel sphere suspended beneath it like a gondola under a balloon. The crew sphere was even more robust than the bathysphere, with walls nearly 4 inches thick and viewing ports made of cone-shaped blocks of plexiglass that grew stronger under pressure rather than weaker. The first deep dive of FNRS-2, conducted in 1948 off the coast of Africa, was both a triumph and a near disaster. The bathyscaphe successfully descended to 4,500 feet, 3 times deeper than the bathysphere had ever gone, proving that the free-diving principle could work. But during the ascent, the vessel began to behave erratically, spinning and tilting in ways that terrified the crew.
The age of robots and remote eyes. As the 20th century progressed, a new approach to deep-sea exploration began to emerge. Instead of sending humans into the crushing depths in protective spheres, why not send mechanical extensions of human senses? Robots that could see and touch and sample the deep ocean while being controlled from the safety of surface ships. The first crude underwater robots, developed in the 1960s and 70s, were simple affairs, essentially cameras and lights mounted on steel frames and connected to surface ships by thick cables. But they could go places and stay there longer than any human-piloted vehicle, and they didn't require the massive life support systems needed for human crews. The development of underwater robotics was driven partly by military needs during the Cold War. Both the United States and Soviet Union needed vehicles that could recover objects from the deep ocean floor, nuclear submarines that had sunk in accidents, weapons that had been lost during tests, and intelligence-gathering equipment that had fallen into enemy hands. The extreme depths and harsh conditions of these recovery operations made human-piloted vehicles impractical. Early ROVs, remotely operated vehicles, were crude but effective. The first successful deep-sea ROV, called Curve, Cable-Controlled Underwater Recovery Vehicle, was developed by the U.S. Navy in the 1960s. Curve looked like a mechanical spider, with a steel frame mounting cameras, lights, and a simple mechanical claw. It was controlled by operators on the surface through an electrical cable that could extend to depths of thousands of feet. Curve's first major success came in 1966, when it recovered a nuclear bomb that had been lost off the coast of Spain during a military aircraft accident. The bomb lay at a depth of nearly 3,000 feet on a steep underwater slope, far too deep and dangerous for human divers to reach safely. Curve operated for weeks in the deep water, first locating the weapon and then carefully securing it for recovery to the surface. This success demonstrated the potential of underwater robotics for deep-sea operations. Unlike human-piloted vehicles, ROVs could work in conditions of extreme depth, cold, and pressure without risking human lives. They could operate for extended periods, limited only by their power supplies and the endurance of their surface support crews. As computer technology advanced, so did these underwater robots. By the 1980s, remotely operated vehicles had become sophisticated enough to manipulate objects on the seafloor, collect samples, and transmit high-definition video of the deep ocean in real time. Advanced ROVs were equipped with multiple cameras, powerful lights, mechanical arms with human-like dexterity, and sensors that could measure temperature, pressure, chemical composition, and other environmental parameters. The most famous of these deep-sea robots was probably Alvin, a manned submersible operated by the Woods Hole Oceanographic Institution. While not technically a robot, it carried human pilots. Alvin represented a new generation of deep-sea vehicles that were smaller, more maneuverable, and more capable than the bathyscapes of the previous era. Alvin was designed specifically for scientific research rather than record-breaking depth achievements. Its maximum operating depth was about 14,000 feet, far shallower than Trieste's record-breaking dive, but it was equipped with sophisticated scientific instruments, sample collection systems, and life support equipment that allowed its crew to work effectively on the sea floor for extended periods. The submersible's small size and maneuverability made it ideal for exploring complex underwater terrain. Unlike the bathyscapes, which could only descend and ascend vertically, Alvin could move horizontally along the sea floor, following geological features and tracking marine life behavior. Its mechanical arms allowed the crew to collect samples, deploy scientific instruments, and interact with the underwater environment in ways that had never been possible before.
It was Alvin that made perhaps the most significant deep-sea discovery of the 20th century. In 1977, while exploring the Galapagos Rift, a region where tectonic plates were spreading apart on the ocean floor, Alvin's crew discovered something that revolutionized our understanding of life on Earth: hydrothermal vents. The discovery happened almost by accident. Alvin was investigating the geological processes occurring at the rift, where new ocean floor was being created by volcanic activity. The crew expected to find a barren landscape of fresh volcanic rock, cooled by the near-freezing water of the deep sea. Instead, they found an underwater oasis teeming with life, unlike anything that had ever been seen before. These underwater geysers, where superheated water rich in minerals erupted from the seafloor, were home to entire ecosystems that existed without any connection to sunlight or photosynthesis. Giant tube worms, some growing to lengths of 8 feet or more, clustered around the vents like underwater trees. Bizarre crabs and shrimp, adapted to temperatures that would instantly cook most organisms, scuttled across the mineral-encrusted surfaces around the vents. Most remarkably, bacteria that derived energy from chemical reactions rather than sunlight formed the base of these vent ecosystems. These chemosynthetic bacteria could process the hydrogen sulfide and other chemicals pouring from the vents, converting them into organic compounds that fed the rest of the vent community. It was a completely different form of primary production than the photosynthesis that drives all surface ecosystems. The discovery of hydrothermal vents showed that the deep ocean wasn't just a cold, dark, largely barren place where a few hardy creatures managed to survive. Instead, it was a complex world with its own energy sources, its own food webs, and its own evolutionary pathways that might have been operating for billions of years. Suddenly, every deep-sea trench, every underwater mountain range, every unexplored region of the ocean floor became a potential site for discoveries that could reshape our understanding of life itself. The deep ocean was revealed to be not just a vast wilderness, but a thriving ecosystem with forms of life and energy production that had never been imagined. The success of Alvin and other deep-sea vehicles also demonstrated the value of combining human intelligence with robotic capability. While purely robotic vehicles could reach greater depths and operate for longer periods, human-piloted submersibles brought the flexibility and intuition of human observers to deep-sea exploration. Scientists aboard Alvin could make instant decisions about what to investigate,
could recognize unusual phenomena that might be missed by programmed sensors, and could adapt their research plans in real time based on what they discovered.
The modern mystery. Today, in the 21st century, we live in an age of unprecedented technological capability. We can see galaxies billions of light years away with space telescopes. We can communicate instantly with people on the other side of the planet. We carry in our pockets computers more powerful than those that sent humans to the moon. And yet, despite all this technological prowess, we've explored less than 5% of our own oceans. This fact seems almost impossible to believe. How can we know more about the surface of Mars than about the deep sea floor of our own planet? How can we have detailed maps of the moon's craters, while vast regions of our ocean floor remain completely unmapped? The answer lies in the fundamental physics that has challenged ocean explorers for centuries. Water is opaque to most forms of electromagnetic radiation. Light, radio waves, and most other signals that work perfectly well in air or space are quickly absorbed by seawater. Even the most advanced satellite can see only a few hundred feet below the ocean's surface on the very clearest days. This means that every piece of information we have about the deep ocean, every map, every photograph, every biological sample, had to be collected by physically sending instruments to the depths and bringing them back. Unlike space exploration, where we can study distant objects with telescopes, ocean exploration requires us to actually go there. The electromagnetic spectrum that allows us to peer across billions of light years of space becomes useless when faced with even a few hundred feet of seawater. Radio waves, which carry our communications to satellites in orbit, are absorbed so quickly with water that submarine communication systems must use extremely low frequencies that can carry only the most basic information. Even these signals can penetrate only a few hundred feet into the ocean. Visible light fares even worse underwater. The brilliant illumination that allows us to see clearly for miles in clear air is reduced to a few hundred feet at most in the clearest ocean water. In typical conditions, visibility underwater is limited to perhaps 50 or 100 feet. In the deep ocean, beyond the reach of sunlight, the darkness is absolute unless artificial lights are provided. This opacity means that most of the remote sensing techniques that have revolutionized our exploration of space and land surfaces simply don't work in the ocean. We cannot use optical telescopes to peer into the deep sea. We cannot use radar or radio astronomy to map underwater features from a distance. We cannot even use most forms of spectroscopy to determine the composition of underwater objects unless we're within a few feet of them. And going there remains incredibly difficult and expensive. The deep ocean is one of the most hostile environments on Earth. The pressure can crush submarines like tin cans. The salt water corrodes metals and damages electronics. The cold saps battery power and makes materials brittle. And if something goes wrong miles below the surface, rescue is often impossible. A single deep-sea expedition can cost millions of dollars and require months of preparation. The specialized vehicles needed for deep ocean work are so expensive that only a handful exist in the entire world. A state-of-the-art deep-sea research submersible costs more than a military fighter jet and requires a highly trained crew of technicians and scientists to operate safely. It's far cheaper to send a probe to Mars than to send a submersible to the deepest parts of our own oceans. A Mars mission can rely on solar power for energy and radio communication for control and data transmission. A deep-sea mission must carry all its power with it in batteries or fuel cells, must use mechanical or acoustic systems for communication, and must be built to withstand pressures that would instantly destroy any spacecraft. But cost and difficulty are only part of the story. The other part is simply scale. Our oceans cover more than 70% of Earth's surface and contain more than 99% of the planet's livable space. The Pacific Ocean alone is larger than all the land areas on Earth combined. If you were to fly across it at the speed of a commercial airliner, it would take you more than 20 hours of continuous flight.
Now imagine that instead of flying over this vast expanse, you had to explore every square mile of its bottom, miles below the surface, in the crushing dark and cold. The magnitude of the task begins to make sense. The ocean covers an area of about 140 million square miles. If we could somehow explore 1 square mile of ocean floor per day, an impossibly optimistic rate given current technology, it would take more than 380,000 years to survey the entire ocean floor. Even with the most advanced technology, a typical deep-sea research expedition might survey a few square miles of ocean floor during a week-long cruise. At this rate, completing a comprehensive survey of the world's oceans would require millions of ship years of effort, more than the entire global research fleet could accomplish in centuries. The three-dimensional nature of the ocean adds another layer of complexity to exploration efforts. Unlike terrestrial exploration, which primarily deals with surface features, ocean exploration must consider the entire water column from surface to seafloor. The deep ocean has layers and zones as distinct as different climate regions on land, each with its own physical conditions, chemical properties, and biological communities. Modern oceanographic surveys must map not just the topography of the seafloor, but also the temperature, salinity, chemical composition, and biological productivity of the water at dozens of different depths. They must track currents, measure the movement of nutrients and pollutants, and monitor how all these factors change over time. It's like trying to create a four-dimensional map of a region larger than all the continents combined. The sheer volume of data generated by modern ocean research creates additional challenges. A single deep-sea expedition might collect terabytes of video footage, acoustic data, water samples, and biological specimens. Processing and analyzing this information requires teams of specialists working for months or years after the expedition returns to shore. Despite these challenges, modern ocean research has made remarkable progress in recent decades. Advanced sonar systems can now map the seafloor with unprecedented detail. Autonomous underwater vehicles can survey large areas without direct human control. Satellite altimetry can detect underwater mountains and valleys by measuring tiny changes in the ocean's surface. But each new discovery seems to reveal how much more there is to learn. Every deep-sea expedition brings back evidence of previously unknown species, unexpected geological features, and complex environmental processes that were never suspected. The deep ocean appears to be far more dynamic, diverse, and interconnected than early explorers ever imagined.
Living darkness. What makes the deep ocean's mystery even more profound is what we've discovered in the tiny fraction we have explored. Every deep-sea expedition brings back evidence of life forms so strange and wonderful that they challenge our very definition of what life can be. In the deepest trenches, where the pressure would instantly crush any surface dweller, scientists have found bacteria that thrive in conditions more extreme than anything we've found on other planets. These organisms have evolved biochemistries so alien that studying them is teaching us new possibilities for how life might exist elsewhere in the universe. Consider the vampire squid, Vampiroteuthis infernalis, whose name literally means vampire squid from hell. Despite that fearsome name, this creature is actually quite gentle, feeding on marine snow, the constant rain of organic matter that drifts down from the surface ocean. But its adaptations to deep-sea life are so extreme that it seems like an organism from another planet. The vampire squid can turn itself inside out when threatened, exposing rows of spines that make it look like a living medieval weapon. It has the largest eyes relative to body size of any animal on Earth, enormous organs designed to gather every possible photon of light in the eternal darkness of the deep sea. Most remarkably, it can control bioluminescent photophores all over its body, creating complex light displays that may serve as camouflage, communication, or defense mechanisms.
In the vast midwater regions, where no sunlight has ever penetrated, creatures have evolved their own forms of illumination. Bioluminescent jellyfish pulse like living galaxies, their transparent bells outlined in cold blue light. Deep-sea fish dangle glowing lures to attract prey in the endless night, like underwater anglers fishing with light instead of bait. The anglerfish family includes some of the most bizarre creatures ever discovered. Female anglerfish grow to be several times larger than males and carry bioluminescent lures that can be controlled with the precision of a spotlight. But even more strange is their reproductive strategy. The tiny males bite into the females and fuse with them permanently, becoming nothing more than sperm-producing organs attached to the female's body. Some organisms create complex patterns of light that may represent forms of communication we're only beginning to understand. The deep-sea hatchetfish has light-producing organs along its belly that it can control individually, creating patterns of bioluminescence that may serve as a form of underwater Morse code. Schools of these fish have been observed flashing in coordinated patterns, suggesting sophisticated group communication systems. In the abyssal plains, the flat, seemingly barren regions that cover most of the deep ocean floor, researchers have discovered that what appears to be empty mud is actually teeming with microscopic life. These organisms process chemicals and cycle nutrients in ways that may be crucial to the health of the entire planet's ecosystem. The abyssal plains were long thought to be biological deserts, regions where life eked out a bare existence by feeding on the sparse organic matter that drifted down from the surface waters. But modern research has revealed these plains to be among the most biologically active regions of the deep ocean.
Bacteria and other microorganisms in abyssal sediments process vast quantities of organic carbon, nitrogen, and other nutrients. They serve as the foundation of deep-sea food webs, supporting communities of worms, crustaceans, and other organisms that have evolved to live in conditions of perpetual darkness and near-freezing temperatures. Some of these sediment-dwelling organisms have evolved remarkable strategies for survival. Certain deep-sea bacteria can remain dormant for decades or even centuries, waiting for favorable conditions before resuming active life. Others have evolved the ability to use alternative energy sources, processing chemicals like sulfur and methane when organic matter is scarce. And in the most extreme environments of all, the hydrothermal vents where superheated water erupts from the Earth's crust, entire communities of organisms exist in conditions that would have been instantly lethal to any life form that scientists knew about before these discoveries. The giant tube worms that cluster around hydrothermal vents represent one of the most remarkable evolutionary adaptations ever discovered. These creatures, which can grow to lengths of 8 feet or more, have no digestive system whatsoever. Instead, they house colonies of chemosynthetic bacteria in specialized organs called trophosome. The bacteria process the chemicals from the vents and provide all the nutrition the worms need to survive. These tube worms live in water temperatures that can exceed 750 degrees Fahrenheit, hot enough to melt lead. Yet they thrive in these conditions, growing faster than almost any other deep-sea organism. Their blood contains specialized proteins that allow them to transport hydrogen sulfide, a gas that would be instantly toxic to most life forms, to their bacterial symbionts. The vent crabs and shrimp that share these extreme environments have evolved equally remarkable adaptations. Some species of vent shrimp have developed specialized organs that can detect infrared radiation, allowing them to navigate the temperature gradients around the vents without being cooked by the superheated water. Each new species discovered in the deep ocean is like finding a new chapter in the book of life on Earth. Some of these organisms may hold keys to medical breakthroughs. The extremophile bacteria from deep-sea vents have already contributed to the development of heat-stable enzymes used in genetic research and industrial processes. Other deep-sea discoveries have led to new understanding of how life might exist on other worlds. The chemosynthetic ecosystems around hydrothermal vents provide a model for how life might evolve around underwater volcanoes on Jupiter's moon Europa or other icy worlds in our solar system. But for every new species we discover, scientists estimate that dozens or hundreds more remain unknown in the unexplored depths. The deep ocean may contain more biodiversity than all the world's rainforests combined, yet we've barely begun to catalog what lives there. Recent genetic studies of deep-sea water samples have revealed the presence of thousands of previously unknown bacterial and archaeo species. Environmental DNA sampling, analyzing genetic material dissolved in seawater, suggests that the microbial diversity of the deep ocean may exceed anything found in terrestrial environments. The discovery of this hidden diversity has profound implications for our understanding of evolution, ecology, and the limits of life. Each new deep-sea organism represents millions of years of evolutionary experimentation, developing unique solutions to the challenges of survival in one of Earth's most demanding environments.
The new explorers. Despite the challenges, a new generation of ocean explorers is pushing the boundaries of what's possible in the deep sea. Advances in materials science have made it possible to build vehicles that can withstand crushing pressures while being lighter and more maneuverable than ever before. Dr. Edith Witter, a marine biologist and deep-sea explorer, has pioneered new techniques for studying bioluminescence in the deep ocean. Her innovative camera systems have captured footage of creatures that have never been filmed before, including the first video of a giant squid in its natural habitat. Witter's work has shown that bioluminescence is far more common and complex in the deep ocean than anyone previously suspected. Witter's e-jelly camera, a device that mimics the bioluminescent display of a deep-sea jellyfish, has revealed that many deep-sea creatures are attracted to specific patterns of light. This discovery has led to new insights into deep-sea behavior and communication, and has provided new tools for studying elusive creatures that avoid conventional lights and cameras. New forms of artificial intelligence allow underwater robots to make decisions and navigate autonomously, exploring areas too dangerous or remote for human-piloted vehicles. These AI systems can recognize and track marine life, identify geological features, and even adapt their exploration strategies based on what they discover. The development of machine learning algorithms specifically designed for underwater exploration has revolutionized how we process and analyze deep-sea data. These systems can identify patterns in acoustic data that reveal the presence of marine life, can recognize geological features that indicate the presence of hydrothermal vents or mineral deposits, and can even predict where new species are most likely to be found. Improvements in battery technology and underwater power systems mean that these robots can stay submerged for weeks or months at a time, systematically mapping and studying areas that were previously inaccessible. Advanced fuel cells and even nuclear power sources are being developed for the most ambitious deep-sea exploration missions. Perhaps most importantly, the cost of deep-sea technology is finally beginning to decrease. What once required the resources of major governments can now be accomplished by universities, research institutions, and even private organizations. This democratization of ocean exploration is beginning to accelerate the pace of discovery. The rise of private companies dedicated to ocean exploration has brought new funding sources and innovative approaches to deep-sea research. Companies like Ocean Infinity and Nekton are developing cost-effective methods for deep-sea mapping and exploration, making it possible for smaller research institutions to conduct sophisticated deep ocean studies. One of the most promising developments is the creation of underwater observation networks, permanent installations on the sea floor that can monitor conditions and collect data continuously. These underwater laboratories are beginning to give us our first real-time, long-term view of how deep-sea ecosystems function and change over time. Bacteria and other microorganisms in abyssal sediments process vast quantities of organic carbon, nitrogen, and other nutrients.
They serve as the foundation of deep-sea food webs, supporting communities of worms, crustaceans, and other organisms that have evolved to live in conditions of perpetual darkness and near-freezing temperatures. Some of these sediment-dwelling organisms have evolved remarkable strategies for survival. Certain deep-sea bacteria can remain dormant for decades or even centuries, waiting for favorable conditions before resuming active life. Others have evolved the ability to use alternative energy sources, processing chemicals like sulfur and methane when organic matter is scarce. And in the most extreme environments of all, the hydrothermal vents where superheated water erupts from the Earth's crust, entire communities of organisms exist in conditions that would have been instantly lethal to any life form that scientists knew about before these discoveries. The giant tube worms that cluster around hydrothermal vents represent one of the most remarkable evolutionary adaptations ever discovered. These creatures, which can grow to lengths of 8 feet or more, have no digestive system whatsoever. Instead, they house colonies of chemosynthetic bacteria in specialized organs called trophosome. The bacteria process the chemicals from the vents and provide all the nutrition the worms need to survive. These tube worms live in water temperatures that can exceed 750 degrees Fahrenheit, hot enough to melt lead. Yet they thrive in these conditions, growing faster than almost any other deep-sea organism. Their blood contains specialized proteins that allow them to transport hydrogen sulfide, a gas that would be instantly toxic to most life forms, to their bacterial symbionts. The vent crabs and shrimp that share these extreme environments have evolved equally remarkable adaptations. Some species of vent shrimp have developed specialized organs that can detect infrared radiation, allowing them to navigate the temperature gradients around the vents without being cooked by the superheated water. Each new species discovered in the deep ocean is like finding a new chapter in the book of life on Earth. Some of these organisms may hold keys to medical breakthroughs. The extremophile bacteria from deep-sea vents have already contributed to the development of heat-stable enzymes used in genetic research and industrial processes. Other deep-sea discoveries have led to new understanding of how life might exist on other worlds. The chemosynthetic ecosystems around hydrothermal vents provide a model for how life might evolve around underwater volcanoes on Jupiter's moon Europa or other icy worlds in our solar system. But for every new species we discover, scientists estimate that dozens or hundreds more remain unknown in the unexplored depths. The deep ocean may contain more biodiversity than all the world's rainforests combined, yet we've barely begun to catalog what lives there. Recent genetic studies of deep-sea water samples have revealed the presence of thousands of previously unknown bacterial and archaeo species. Environmental DNA sampling, analyzing genetic material dissolved in seawater, suggests that the microbial diversity of the deep ocean may exceed anything found in terrestrial environments. The discovery of this hidden diversity has profound implications for our understanding of evolution, ecology, and the limits of life. Each new deep-sea organism represents millions of years of evolutionary experimentation, developing unique solutions to the challenges of survival in one of Earth's most demanding environments.
The new explorers. Despite the challenges, a new generation of ocean explorers is pushing the boundaries of what's possible in the deep sea. Advances in materials science have made it possible to build vehicles that can withstand crushing pressures while being lighter and more maneuverable than ever before. Dr. Edith Witter, a marine biologist and deep-sea explorer, has pioneered new techniques for studying bioluminescence in the deep ocean. Her innovative camera systems have captured footage of creatures that have never been filmed before, including the first video of a giant squid in its natural habitat. Witter's work has shown that bioluminescence is far more common and complex in the deep ocean than anyone previously suspected. Witter's e-jelly camera, a device that mimics the bioluminescent display of a deep-sea jellyfish, has revealed that many deep-sea creatures are attracted to specific patterns of light.
This discovery has led to new insights into deep-sea behavior and communication, and has provided new tools for studying elusive creatures that avoid conventional lights and cameras. New forms of artificial intelligence allow underwater robots to make decisions and navigate autonomously, exploring areas too dangerous or remote for human-piloted vehicles. These AI systems can recognize and track marine life, identify geological features, and even adapt their exploration strategies based on what they discover. The development of machine learning algorithms specifically designed for underwater exploration has revolutionized how we process and analyze deep-sea data. These systems can identify patterns in acoustic data that reveal the presence of marine life, can recognize geological features that indicate the presence of hydrothermal vents or mineral deposits, and can even predict where new species are most likely to be found. Improvements in battery technology and underwater power systems mean that these robots can stay submerged for weeks or months at a time, systematically mapping and studying areas that were previously inaccessible. Advanced fuel cells and even nuclear power sources are being developed for the most ambitious deep-sea exploration missions. Perhaps most importantly, the cost of deep-sea technology is finally beginning to decrease. What once required the resources of major governments can now be accomplished by universities, research institutions, and even private organizations. This democratization of ocean exploration is beginning to accelerate the pace of discovery. The rise of private companies dedicated to ocean exploration has brought new funding sources and innovative approaches to deep-sea research. Companies like Ocean Infinity and Nekton are developing cost-effective methods for deep-sea mapping and exploration, making it possible for smaller research institutions to conduct sophisticated deep ocean studies. One of the most promising developments is the creation of underwater observation networks, permanent installations on the sea floor that can monitor conditions and collect data continuously. These underwater laboratories are beginning to give us our first real-time, long-term view of how deep-sea ecosystems function and change over time.
The Ocean Observatories Initiative, a network of cabled observatories on the seafloor off the Pacific Northwest, provides continuous power and internet connectivity to deep-sea instruments. For the first time, scientists can monitor deep-sea conditions in real time, watching how ecosystems respond to changes in temperature, chemistry, and other environmental factors. These observatory networks have already revealed that the deep ocean is far more dynamic than anyone suspected. Underwater storms move across the abyssal plains, stirring up sediments and redistributing marine life. Deep-sea currents shift and change in response to surface weather patterns and seasonal cycles. Even the deepest parts of the ocean show daily and seasonal rhythms that were completely unknown before continuous monitoring became possible. Another exciting development is the use of environmental DNA sampling, which allows scientists to detect the presence of organisms without actually seeing them. By analyzing water samples for genetic material, researchers can identify species that might be too rare or elusive to observe directly, giving us a much more complete picture of deep-sea biodiversity. Environmental DNA, or eDNA, techniques have revolutionized our understanding of deep-sea ecosystems. A single water sample can contain genetic material from hundreds of different species: bacteria, archaea, protists, fish, and invertebrates that live in the water column or on nearby sea floor. This technique has revealed that deep-sea biodiversity is far greater than traditional sampling methods had suggested. The development of real-time genetic sequencing technologies means that scientists can now identify species while still at sea, allowing them to adapt their sampling strategies based on what they discover. This has led to the discovery of entirely new groups of organisms and has revealed complex ecological relationships that were previously unknown. Advanced material science has also contributed to the new generation of deep-sea exploration tools. Carbon fiber composites and syntactic foams allow the construction of vehicles that are both incredibly strong and relatively lightweight. New types of pressure-resistant electronics can operate at depths that would have destroyed earlier systems. The development of ceramic and metallic glass materials has created new possibilities for deep-sea construction.
These materials can withstand crushing pressures while maintaining their structural integrity, opening up possibilities for permanent deep-sea installations and habitats. But perhaps the most significant change in modern ocean exploration is the growing recognition of how crucial the deep sea is to the health of our entire planet. The deep ocean plays a vital role in regulating Earth's climate, storing vast amounts of carbon dioxide, and driving the currents that distribute heat around the globe. Understanding how these systems work and how they might be affected by human activities has become one of the most pressing scientific questions of our time. The deep ocean isn't just a realm of scientific curiosity, it's a critical component of the planetary systems that make Earth habitable for all life. Climate scientists have discovered that the deep ocean acts as Earth's primary carbon reservoir, storing more than 50 times as much carbon as the atmosphere. Changes in deep ocean circulation patterns can dramatically affect global climate by altering how much carbon dioxide the oceans can absorb from the atmosphere. The thermohaline circulation, the global system of deep ocean currents driven by differences in temperature and salinity, transports heat from the tropics to polar regions and helps regulate global climate patterns. This circulation system depends on processes that occur in the deep ocean, including the formation of deep water masses in polar regions and the upwelling of deep water in tropical and temperate zones. Recent research has shown that this deep circulation system is changing in response to global warming, with potentially significant consequences for future climate patterns. Understanding these changes requires detailed knowledge of deep ocean conditions that can only be obtained through direct exploration and monitoring.
The frontier within. As we near the end of our journey into the story of deep-sea exploration, it's worth reflecting on what this last great frontier means for humanity. In an age when we sometimes feel that everything has been discovered, every frontier conquered, every mystery solved, the deep ocean reminds us that our own planet still holds wonders beyond imagination. There's something profoundly humbling about the fact that creatures living just a few miles beneath the surface of our own world remain as alien to us as anything we might imagine on distant planets. It suggests that the universe's capacity for surprise and wonder is far greater than we often suppose. The deep ocean teaches us that exploration is not just about reaching new places, it's about understanding the complexity and interconnectedness of the world we inhabit. Every deep-sea expedition reveals new connections between the deepest parts of the ocean and the surface world where we live. The nutrients that support marine food webs begin their journey in the deep ocean, where bacterial decomposition releases essential elements back into the water column. The oxygen that deep-sea creatures breathe was produced by photosynthesis at the surface, then carried to the depths by currents that may take centuries to complete their circulation. Even the weather patterns that affect our daily lives are influenced by processes that occur in the deep ocean. The heat stored in deep water masses affects the intensity of hurricanes and typhoons. The carbon dioxide absorbed by the deep ocean influences atmospheric composition and global climate patterns. The deep ocean also teaches us about the limits of human knowledge and technology. For all our scientific advances, we are fundamentally surface dwellers, adapted to a narrow range of temperature, pressure, and atmospheric conditions. The deep sea represents environments so extreme that we can visit them only briefly and at great expense, like astronauts visiting space. This limitation has forced us to develop new ways of understanding and interacting with environments that we cannot directly inhabit. The technologies developed for deep-sea exploration, remote sensing systems, autonomous vehicles, pressure-resistant materials, have found applications in space exploration, medical research, and industrial processes. But perhaps most importantly, the deep ocean represents hope. In a world where natural habitats are disappearing and species are becoming extinct at alarming rates, the deep sea remains a vast repository of life that we're only beginning to understand. The organisms that live in the deepest parts of our oceans have survived ice ages, asteroid impacts, and countless other catastrophes over millions of years. They represent life's incredible resilience and adaptability. The same forces that made deep-sea exploration so difficult, the crushing pressure, the eternal darkness, the extreme cold, have also created opportunities for life to evolve in ways we never imagined possible. Every deep-sea expedition brings back not just new species and new scientific data, but new stories of life's endless creativity. These stories expand our understanding of what's possible, not just for life in Earth's oceans, but for life anywhere in the universe. The extremophile bacteria discovered around hydrothermal events have taught us that life can derive energy from chemical reactions we once thought were too harsh to support living organisms. This knowledge has expanded our understanding of where life might exist on other worlds, in the subsurface oceans of icy moons, around hydrothermal systems on other planets, or in environments that we haven't yet imagined. The bioluminescent communication systems of deep-sea creatures have inspired new technologies for underwater communication and lighting. The pressure-resistant biochemistries of deep-sea organisms have led to new understanding of protein structure and function. The symbiotic relationships between deep-sea animals and chemosynthetic bacteria have revealed new possibilities for biological energy production. As we face environmental challenges that sometimes seem overwhelming, the deep ocean reminds us that life has incredible powers of persistence and creativity. The same planet that gave us life continues to nurture forms of life so strange and beautiful that discovering them is like finding magic made real. The call of the deep. Tonight, as you drift toward sleep, imagine yourself standing once again on that familiar shoreline where our journey began. But now you see the ocean with different eyes. You understand that beneath those familiar waves lies a world as vast and mysterious as the night sky above. You know now why the deep sea has remained unexplored for so long, not because humans lacked courage or curiosity, but because the very physics of water created barriers that took centuries of ingenuity to overcome. You've walked alongside the inventors and dreamers who gradually pushed deeper and deeper into the ocean's mysteries, each generation building upon the discoveries of those who came before. You've seen how a simple diving bell led to pressurized suits, how balloonist principles enabled the first free-diving bath escape, how advances in robotics and artificial intelligence are finally beginning to make systematic exploration of the deep ocean possible. But you've also learned that this story is far from over. The deep ocean remains Earth's greatest frontier, holding secrets that may revolutionize our understanding of life, climate, and our planet's future. In the deepest places, life persists in forms so strange and wonderful that they expand our very definition of what life can be. The story of deep-sea exploration is also a story of human persistence and ingenuity. From Halley's wooden diving bell to modern autonomous underwater vehicles, each advance has required overcoming seemingly impossible technical challenges. The crushing pressure of the deep sea has forced us to develop new materials, new power systems, new ways of communicating and navigating in environments where conventional technologies fail. This technological innovation has had benefits that extend far beyond ocean exploration. The life support systems developed for deep-sea vehicles have contributed to spacecraft design. The pressure-resistant materials created for deep ocean use have found applications in everything from medical devices to industrial equipment. The autonomous navigation systems developed for underwater robots have influenced the development of self-driving cars and other automated systems. As ocean explorers continue their work, pushing ever deeper into the blue-black mysteries beneath the waves, they are not just mapping the seafloor or cataloging new species. They are expanding the boundaries of human knowledge and wonder. They are showing us that our home planet still holds surprises that rival anything we might discover among the stars. The next time you stand beside the ocean, remember this story. Remember that beneath those rolling waves lies a world more alien and wonderful than any science fiction writer has ever imagined. A world where creatures generate their own light in the eternal darkness, where life thrives in conditions that would instantly destroy any surface dweller, where the very rocks of the sea floor give birth to oases of impossible life. And remember that this world, alien as it seems, is part of the same planet that gave birth to all life on Earth. The same evolutionary forces that created the flowers in your garden and the birds in your sky also created the bizarre and beautiful creatures of the deep sea. They are our distant cousins, sharing with us the same ancient heritage of life's first stirring in Earth's primordial oceans. The deep sea remains unexplored not because we lack the technology or the will to explore it, but because it represents a frontier so vast and challenging that it will likely take centuries more to fully understand. Each generation of ocean explorers adds new chapters to this ongoing story of discovery, gradually illuminating one of the last great mysteries of our home planet. The network builders. As deep-sea exploration technology advanced, a new vision began to emerge among ocean scientists. Instead of making occasional visits to the deep ocean, why not establish permanent observation posts that could monitor conditions continuously? This idea led to one of the most ambitious engineering projects of the late 20th century, the creation of underwater cable networks that could power instruments and transmit data from the deep sea floor to research stations on land. The challenges were immense. Underwater cables had to withstand crushing pressure, resist corrosion from salt water, and maintain reliable electrical connections across distances of hundreds or thousands of miles. They had to survive storms, earthquakes, and the occasional ship's anchor dragging across the sea floor. The engineering solutions developed for these networks drew upon decades of experience with undersea telegraph and telephone cables, but the requirements for deep-sea research networks were far more demanding. Telegraph cables needed to carry only simple electrical signals, while research networks required the ability to transmit enormous amounts of digital data while simultaneously providing power to complex instrument packages. The first successful deep-sea cable systems were adaptations of the undersea telegraph cables that had connected continents since the 1860s. The original transatlantic cable, laid in 1866, demonstrated that it was possible to maintain electrical connections across thousands of miles of ocean floor. But these early cables carried only simple electrical pulses that could be decoded as text messages. Modern deep-sea research networks required cables capable of transmitting terabytes of data per day, video feeds from underwater cameras, acoustic data from sonar systems, chemical measurements from environmental sensors, and real-time communication with autonomous underwater vehicles. They also needed to provide electrical power to instruments that might be thousands of miles from the nearest land-based power source. The Neptune project, begun in the early 2000s off the coast of British Columbia, was one of the first successful attempts to create a permanent deep-sea research network. A main cable carried power and data connections from shore to a series of underwater junction boxes, which in turn connected to scientific instruments spread across hundreds of square miles of seafloor. The system worked like an underwater version of the Internet, with data packets traveling from deep-sea instruments through fiber optic cables to surface stations, where they could be transmitted to research institutions around the world. For the first time, scientists could monitor deep-sea conditions in real time from their laboratories, watching underwater volcanic eruptions as they happened, and tracking the movement of marine life across vast areas of ocean floor. The engineering challenges of building Neptune were staggering. The main cable had to be laid across underwater canyons deeper than the Grand Canyon, across active earthquake faults, and through areas where underwater landslides were common. The junction boxes had to be designed to operate reliably for decades in conditions of crushing pressure, near freezing temperatures, and complete darkness. Each junction box was essentially a deep-sea power station and data center, about the size of a small car, and built to withstand pressures that would instantly crush any surface vehicle. They contained transformers to convert electrical power to the voltages needed by different instruments, computer systems to route data from multiple sources, and backup systems to maintain operations if primary systems failed. For the first time, scientists could monitor deep-sea conditions continuously, watching how ecosystems changed with the seasons, how geological processes operated over long timescales, and how marine life responded to environmental changes. The data streaming back from these underwater networks revealed that the deep ocean was far more dynamic and variable than anyone had suspected. The success of Neptune inspired similar projects around the world. The European Seas Observatory Network, ESONET, connected research instruments across multiple deep-sea sites in the Atlantic and Mediterranean. The Ocean Observatories Initiative in the United States established cabled observatories off both the Atlantic and Pacific coasts. These networks began to reveal the deep ocean as a world of constant change and activity. Underwater storms, invisible from the surface, moved across the abyssal plains with the force of terrestrial hurricanes, stirring up sediments and redistributing nutrients across vast areas. Deep-sea currents shifted and changed in response to surface weather patterns, seasonal cycles, and long-term climate variations. The continuous monitoring capabilities of these networks also revealed the interconnectedness of surface and deep-sea processes. Changes in surface temperature and chemistry were quickly transmitted to the deep ocean through downwelling currents. Nutrients released by deep-sea bacterial activity eventually reached the surface through upwelling currents, supporting photosynthetic organisms thousands of miles away. Perhaps most importantly, these networks provided the first real-time view of how deep-sea ecosystems responded to human activities. They detected changes in ocean chemistry caused by increased atmospheric carbon dioxide, tracked the movement of pollutants from surface to deep waters, and monitored how marine life adapted to changing environmental conditions. The Deep Ocean Observing Strategy, DOS, an international coordination effort, began working to connect these regional networks into a global system for monitoring the world's deep oceans. This vision of a planet-wide network of deep-sea observatories represented one of the most ambitious scientific projects ever attempted, a system that could provide real-time data about conditions in the most remote and inaccessible parts of Earth's biosphere.
The biological revolution. While engineers were building better vehicles and establishing monitoring networks, marine biologists were making discoveries that revolutionized our understanding of life itself. Each new deep-sea expedition brought back evidence of organisms so strange and wonderfully adapted to extreme conditions that they challenged fundamental assumptions about biology. The discovery of chemosynthetic bacteria around hydrothermal vents was just the beginning. As researchers studied these organisms more closely, they realized that life based on chemical energy rather than sunlight might be far more common than anyone had suspected. In fact, some scientists now believe that chemosynthetic organisms might represent a larger biomass than all photosynthetic life combined. Dr. Sylvia Earle, one of the most influential deep-sea researchers of the late 20th century, often described the feeling of descending into the deep ocean as like traveling to an alien planet. But unlike the sterile landscapes of Mars or the Moon, this alien world was teeming with life forms that had evolved solutions to survival challenges that no surface organism had ever faced. Earle's pioneering work in deep-sea exploration began in the 1960s, when she was one of the first scientists to use scuba diving equipment for serious marine research. Her observations of underwater ecosystems led her to recognize that the ocean was far more complex and fragile than most people understood. In 1979, Earle set a world record for the deepest solo dive, descending to 1,250 feet in a specialized atmospheric diving suit. Her descriptions of the deep-sea environment she encountered challenged prevailing assumptions about what the deep ocean was like. "The deep sea is not a desert," Earle wrote. "It's a rainforest of the most extraordinary kind. A three-dimensional forest where every level has its own community of creatures, its own adaptations, its own solutions to the challenges of life in the depths." Consider the problem of pressure. At depths of 20,000 feet, the pressure is nearly 600 times greater than at sea level. This pressure would instantly collapse any air-filled space and would compress most materials to a fraction of their surface size. Yet deep-sea fish swim through these crushing depths as easily as surface fish navigate shallow water. How do they do it? The answer lies in some of the most elegant biological adaptations ever discovered. Deep-sea fish have no air-filled swim bladders, which would be crushed instantly. Instead, they maintain buoyancy through specialized oils and proteins that are incompressible. Their cell membranes contain unique fatty acids that remain flexible under pressure. Their enzymes are modified to function efficiently in conditions that would instantly denature the proteins in surface organisms. The pressure-resistant proteins found in deep-sea organisms work through several mechanisms. Some have evolved more flexible structures that can bend and twist without breaking under pressure. Others contain specialized amino acid sequences that help them maintain their shape even when compressed. Still others are stabilized by interactions with other molecules that help them resist pressure-induced changes.
The study of these pressure-adapted organisms led to breakthroughs in biotechnology and medicine. Enzymes from deep-sea bacteria proved valuable for industrial processes that required high pressure or extreme conditions. These piezophilic, pressure-loving enzymes could catalyze chemical reactions under conditions that would destroy conventional enzymes. Proteins from deep-sea organisms became models for developing new materials and medicines. Scientists learned how to engineer artificial proteins with enhanced stability and resistance to environmental stress. These advances have led to new types of medical implants, industrial catalysts, and research tools. But the biological surprises didn't stop with pressure adaptation. Researchers discovered that many deep-sea organisms had evolved forms of bioluminescence far more sophisticated than anything found in surface environments. Some deep-sea jellyfish create complex light displays that may serve as communication systems. Certain deep-sea fish use bioluminescent lures not just to attract prey, but to create elaborate courtship displays in the darkness. The bioluminescent systems of deep-sea organisms operate on principles that are only now being understood. Most use the reaction between luciferin, a light-producing compound, and luciferase, an enzyme that catalyzes the reaction, to produce cold light with very little waste heat. But the specific chemicals and mechanisms vary enormously between different species and different body parts. Some deep-sea creatures can control the color, intensity, and pattern of their bioluminescence with remarkable precision. The deep-sea squid Tangia danae has bioluminescent organs on its arms that it can flash in complex patterns, possibly to communicate with other squid or to confuse predators and prey. The study of these bioluminescent systems led to the development of new research tools and medical techniques. The green fluorescent protein, GFP, originally isolated from deep-sea jellyfish, became one of the most important tools in modern biological research, allowing scientists to track the movement of specific proteins within living cells. GFP and related fluorescent proteins have revolutionized cell biology, genetics, and medical research. They allow researchers to visualize cellular processes in real time, track the development of embryos, and monitor the progression of diseases. The discovery and development of these proteins led to the 2008 Nobel Prize in Chemistry. Even more remarkable were the discoveries of organisms that seemed to violate basic principles of biology. Researchers found bacteria that could survive in temperatures approaching the boiling point of water, organisms that could metabolize sulfur compounds that would be toxic to most life, and creatures that could remain dormant for decades or centuries before resuming active life when conditions became favorable. The extremophile bacteria discovered in deep-sea environments have expanded our understanding of the limits of life. Some can survive in temperatures above 250 degrees Fahrenheit, pressures thousands of times greater than at sea level, and chemical conditions that would be instantly lethal to most organisms. These discoveries have forced biologists to reconsider fundamental questions about what conditions are necessary for life. Thermus aquaticus, a bacterium originally discovered in hot springs but later found around deep-sea hydrothermal vents, produces an enzyme called Taq polymerase that remains stable at high temperatures. This enzyme became essential for the polymerase chain reaction, or PCR, a technique used to amplify DNA that is fundamental to modern genetics, forensics, and medical diagnosis. These discoveries had profound implications for astrobiology, the search for life elsewhere in the universe. If life could thrive in the extreme conditions of Earth's deep ocean, then perhaps it could also exist in the subsurface oceans of Jupiter's moon Europa, or in the methane lakes of Saturn's moon Titan, or in environments on other worlds that we haven't even imagined. The deep sea was teaching us that life's possibilities were far greater than we had ever imagined. Every expedition brought back evidence of organisms that pushed the boundaries of what scientists thought was possible for living things to survive and thrive. The map makers of the abyss. While biologists were discovering new forms of life, another group of scientists was working to create the first detailed maps of the deep ocean floor. This seemingly straightforward task turned out to be one of the most challenging mapping projects in human history. The problem wasn't just the darkness and crushing pressure of the deep ocean, it was scale. The ocean floor covers an area larger than all the continents combined, and every square mile of it had to be mapped using ships that could travel only slowly across the surface. Using sonar systems, they could scan only narrow strips of seafloor with each pass. Marie Tharp, working in the 1950s and 60s with her colleague Bruce Heezen, became one of the first people to create comprehensive maps of the ocean floor. Working from sonar data collected by research vessels, she hand-drew detailed charts that revealed underwater mountain ranges, deep canyons, and vast abyssal plains. Tharp's work was groundbreaking not just for its scientific accuracy, but for the way it revealed the ocean floor as a landscape as varied and dramatic as any found on land. Her maps showed underwater mountain ranges that dwarfed the Himalayas, canyons deeper than the Grand Canyon, and plains that stretched for thousands of miles without significant elevation change. But Tharp faced significant challenges beyond the technical difficulties of deep-sea mapping. As a woman working in the male-dominated field of marine geology in the 1950s, she was often excluded from research cruises and had to work with data collected by others. Many of her male colleagues initially dismissed her interpretations of the sonar data, particularly her suggestion that there was a continuous underwater mountain range running down the center of the Atlantic Ocean. Tharp's insight about the mid-Atlantic ridge was based on careful analysis of thousands of depth measurements collected by research vessels over many years. She noticed that there was a consistent pattern of underwater mountains running roughly north-south down the center of the Atlantic, with a deep valley or rift running along the crest of the mountain range. Her maps were more than just scientific tools. They were works of art that captured the dramatic landscape hidden beneath the waves. Her map of the Mid-Atlantic Ridge, published in 1957, showed for the first time the underwater mountain chain that runs down the center of the Atlantic Ocean like a backbone. The artistic quality of Tharp's maps was not accidental. She understood that scientific data needed to be presented in ways that would engage the imagination and help people visualize the hidden landscape of the ocean floor. Her hand-drawn charts used shading, perspective, and artistic techniques to make the underwater terrain come alive. But Tharp's maps also revealed something unexpected. The ocean floor wasn't a flat, featureless plain as many had assumed. Instead, it was a landscape as varied and dramatic as any mountain range on land. There were underwater canyons deeper than the Grand Canyon, mountain peaks taller than Mount Everest, and vast plains that stretched for thousands of miles without significant elevation change. The mapping of the ocean floor led to one of the most important geological discoveries of the 20th century, the theory of plate tectonics. The patterns revealed by Tharp and other ocean mappers showed that the Earth's surface was divided into moving plates, and that the ocean floor was constantly being created at underwater mountain ridges and destroyed at deep trenches. This discovery revolutionized geology, explaining everything from earthquakes and volcanic activity to the distribution of continents and the formation of mountain ranges. It showed that the Earth was a dynamic, constantly changing planet, with processes operating on timescales of millions of years. The underwater mountain ranges that Tharp mapped turned out to be the boundaries between tectonic plates, where new ocean floor was being created by volcanic activity. The deep trenches she identified were the places where old ocean floor was being subducted back into the Earth's interior. The patterns of earthquakes and volcanic activity around the world suddenly made sense when viewed in the context of these moving plates. Modern ocean mapping uses satellite altimetry, multi-beam sonar, and autonomous underwater vehicles to create increasingly detailed charts of the seafloor. Satellite altimetry works by measuring tiny changes in sea level caused by the gravitational pull of underwater mountains and valleys. This technique can detect large-scale features of the ocean floor from space, but cannot provide the detailed mapping needed for many scientific and commercial purposes. Multibeam sonar systems mounted on research vessels can map strips of seafloor with resolution measured in meters rather than kilometers. These systems emit fans of sound waves that bounce off the seafloor and return to the ship, allowing computers to calculate the depth and shape of underwater features with unprecedented accuracy. Autonomous underwater vehicles, AUVs, equipped with high-resolution sonar, can map the seafloor with even greater detail, creating charts that show features as small as individual rocks or coral formations. These vehicles can operate independently for days or weeks, systematically surveying large areas of seafloor without requiring constant supervision from surface ships. But even today, with all our advanced technology, we have detailed maps of less than 20% of the ocean floor. The remaining 80% remains as mysterious as the surface of an alien planet. Most of our knowledge of the deep ocean floor comes from satellite altimetry data that provides only a rough outline of major features. The Seabed 2030 project, launched in 2017, aims to create a complete map of the world's ocean floor by 2030. This ambitious international collaboration represents the largest mapping project in human history, requiring the coordination of research vessels, underwater vehicles, and data processing centers around the world. The project faces enormous challenges. To map the entire ocean floor at the resolution needed for scientific research would require thousands of ship years of effort. Even with the most advanced technology, research vessels can map only about 100 square miles of seafloor per day under ideal conditions. At this rate, completing a comprehensive survey of the world's 140 million square miles of ocean floor would take centuries. The Seabed 2030 project is addressing these challenges through innovative approaches to data collection and processing. They're working with commercial shipping companies to equip merchant vessels with bathymetric, depth-measuring equipment, turning the global shipping fleet into a crowdsourced ocean mapping network. They are also developing new autonomous underwater vehicles that can operate independently for months at a time, systematically surveying remote areas of ocean floor without requiring constant supervision from surface ships. But even when this project is completed, the maps will show only the basic topography of the ocean floor. Understanding what these underwater landscapes mean, how they were formed, how they affect ocean currents and marine life, how they might change in the future, will require centuries of additional research. The completed maps will reveal the true extent of underwater mountain ranges, the locations of previously unknown seamounts and ocean trenches, and the detailed structure of underwater features that affect everything from ocean circulation to marine ecosystems. This information will be crucial for understanding climate change, managing marine resources, and protecting underwater habitats.
The treasure hunters and the archaeologists. The deep ocean holds more than just scientific mysteries. It also contains some of humanity's most precious historical artifacts. Every shipwreck that has ever sunk into deep water carries with it a frozen moment in human history, preserved by the cold, dark, oxygen-poor conditions of the deep sea. The most famous of these underwater time capsules is, of course, the RMS Titanic. When Robert Ballard's team discovered the wreck in 1985, lying broken on the sea floor at a depth of 12,500 feet, they found a ship that had been perfectly preserved for more than 70 years. The cold water and lack of oxygen had prevented the normal decay processes that would have destroyed the wreck in shallower water. Ballard's discovery of the Titanic was the culmination of a decades-long search that had captured the public imagination. The ship, which sank on its maiden voyage in 1912 after striking an iceberg, had become a symbol of human hubris and technological failure. Finding the wreck required developing new technologies for deep-sea exploration and navigation. The search for the Titanic pushed the boundaries of deep-sea archaeological technology. Ballard and his team used a combination of towed cameras, autonomous underwater vehicles, and advanced sonar systems to locate the wreck on the vast abysmal plain of the North Atlantic. The discovery proved that even the most challenging deep-sea archaeological projects were possible with sufficient technology and determination. But the Titanic was just the beginning. As deep-sea exploration technology improved, archaeologists began to realize that the deep ocean contained thousands of shipwrecks from every era of human seafaring. Ancient Roman vessels carrying amphorae full of wine and olive oil, medieval trading ships loaded with spices and precious metals, modern warships from the great conflicts of the 20th century. Each wreck told a story, not just of the ship and its cargo, but of the people who built it, sailed it, and died with it. The deep ocean had become humanity's largest museum, filled with artifacts that could teach us about ancient trade routes, shipbuilding techniques, and daily life in past eras. The preservation conditions in the deep ocean are remarkable. The combination of cold temperatures, high pressure, and low oxygen levels creates an environment where organic materials can survive for centuries or millennia. Wooden ships that would have rotted away in shallow water remain structurally intact on the deep-sea floor. Textiles, leather, and even paper documents can survive in recognizable form. But deep-sea archaeology presented unique challenges. Every artifact had to be carefully mapped and documented before removal, as the extreme conditions made it impossible to return for additional study. The pressure and cold meant that recovery operations had to be planned with military precision, and mistakes could destroy irreplaceable historical evidence.
The development of ROVs, remotely operated vehicles, revolutionized underwater archaeology. These robotic systems could spend hours examining wreck sites, taking detailed photographs, and carefully extracting artifacts without risking human lives. Advanced ROVs could manipulate objects with the precision of human hands, while being controlled by operators safely on the surface. Modern archaeological ROVs are equipped with high-definition cameras, precision manipulator arms, and specialized tools for excavation and artifact recovery. They can create detailed three-dimensional maps of wreck sites, allowing archaeologists to study the spatial relationships between artifacts and understand how the site was formed. Some of the most significant archaeological discoveries came from unexpected sources. Commercial fishing vessels occasionally brought up ancient artifacts in their nets. Oil exploration companies discovered shipwrecks while surveying the seafloor for drilling sites. Even treasure hunters, despite their often commercial motivations, contributed to our understanding of maritime history. The discovery of ancient shipwrecks also revealed information about sea level changes, climate patterns, and ocean currents throughout history. Ships that sank in what are now deep water sometimes revealed that sea levels were much lower in the past, or that ocean currents flowed in different patterns than they do today. Some of the most important deep-sea archaeological discoveries have come from the Mediterranean Sea, where thousands of years of maritime trade have left a rich legacy of shipwrecks. The Uluburun shipwreck, discovered off the coast of Turkey, dates to the Late Bronze Age, around 1300 BCE, and contained artifacts from across the ancient world: copper ingots from Cyprus, tin from Afghanistan, ivory from Africa, and amber from the Baltic Sea. The Antikythera wreck, discovered in 1900 by Greek sponge divers, contained one of the most remarkable artifacts ever recovered from the sea: a complex mechanical device now known as the Antikythera mechanism. This bronze calculator, dating to around 100 BCE, could predict the positions of the sun, moon, and planets with remarkable accuracy. Its discovery revolutionized our understanding of ancient Greek technology and scientific knowledge. But deep-sea archaeology also raised difficult questions about ownership and preservation. Who owns a shipwreck that sank in international waters centuries ago? Should artifacts be preserved in their original location or brought to the surface for study and display? How can the scientific value of archaeological sites be balanced against the commercial interests of salvage companies?
These questions became more pressing as deep-sea technology made more wrecks accessible. The development of commercial deep-sea salvage operations led to conflicts between archaeologists who wanted to preserve wreck sites for scientific study and treasure hunters who were interested primarily in recovering valuable artifacts for sale. International treaties and laws struggled to keep pace with the technological possibilities, leading to conflicts between archaeologists, governments, salvage companies, and descendants of the people who died in historical shipwrecks. The 2001 UNESCO Convention on the Protection of the Underwater Cultural Heritage established international standards for underwater archaeology, but enforcement remains challenging in international waters. The debate over the Titanic itself illustrates these challenges. While the wreck is protected by international treaty, the site has been visited by numerous expeditions that have removed thousands of artifacts. Some argue that these artifacts should be preserved in museums where they can be studied and displayed. Others contend that the wreck site itself is a memorial that should remain undisturbed. Modern underwater archaeology has moved toward a preservation-first approach, using non-invasive techniques to study wreck sites without removing artifacts. High-resolution photography, 3D mapping, and virtual reality technologies allow researchers to create detailed records of archaeological sites that can be studied indefinitely without disturbing the original artifacts.